Bismillah ar-Rahman ar-Rahim. Assalamu alaikum rahmatullah. Peace and blessings upon you all. Dear students, last time we gave the introduction of the deadlock, but today we continue with the deadlock. Okay, and in deadlock we said actually basically we need to have four conditions like mutual exclusion, hold and wait, no preemption, and circular wait. All of the four to be there so that we can have a deadlock, right? So we say technically we say if we have a resource one and we got to have a resource 2 for example, and we say a thread 1 or process 1, so let me call it thread 1, this is the thread second. Okay, if resource 1 is being owned by the thread 1 and it's asking for the resource 2, so it is waiting for resource 2. Okay, now this resource 2 is actually given to the T2 thread second, and it's waiting for the resource 1. So this is a circular wait, holding one resource and asking for another, and there is no preemption in the resource because this is the resource may be non-preemptive, you can't leave it, so you are holding it and asking for other, so you are having a deadlock situation. For example, we read some semaphores, right? So if we do, for example, there is a process A and process 1 maybe and process 2. Okay, so let us have for two resources, maybe there's a printer and there's a disk. Okay, so I have a semaphore P and semaphore D for the printer and for the disk. Okay, if you don't understand this, go back and see the semaphore video. Okay, and this process A, say for example, comes in, process 1 it is, okay, process 1 comes in and it does wait on the printer. So if printer is free, so initially it is equal to 1, this will be also equal to 1, so they are both free for example right now, and both processes come simultaneously, and the process 2 does wait on the disk. Okay, now what will happen, wait on P is, if P is greater than 0, it will decrement it, make it 0 and lock it, so we can do it because it's free, and disk is also free, that's also equal to 1, you can do it. So P2 can do the wait on disk, so it will decrement it actually, okay, and make it 0. So in both cases P will be 0 and D will be 0, right? Now they are locked. Now maybe after this the P1 will do the wait on the D and this guy does the wait on the P, if this is the situation. After that we can our signal back, if we are done with this we can signal the P as well as we'll signal the D. Okay, and here also we can signal the D and we can signal the P. Now question is, when this is done, it's okay, we have locked it, and this guy does D, wait on D, we can do it because D was 1, so make it 0. Now this guy is trying to do wait on the D, but that is locked, so what will happen, it will sleep, okay, until some process who has done the wait on the D will leave the lock, will do signal on the D. That means this will happen here, and you can come out of this sleep queue here. And P2 is doing the wait on the P, and that means it's sleeping on the semaphore variable P, so it's thinking that some process who has done wait on P will do the signal on the P here, and it can come out of this sleep. So this guy is technically waiting for the P2, and P2 is sleeping and waiting for the P1 to release the P. So both of these guys are sleeping. Okay, so both of them go into sleep queue. Now when both of them go in sleep queue, neither P1 releases the printer and neither P2 releases the disk. So they are both in a deadlock, they will never come out of it. So this is a situation of perfectly the deadlock. Okay, so we already understood what is deadlock, and this was given more information. Now how to represent deadlock graphically. So we need to have a graphical representation. Okay, for that what we have is resource allocation graph. So the resource allocation graph is it is the resource allocation graph. The resource allocation graph G is actually set of two V is it contains nodes, okay, and it contains the edges, okay. Now this V nodes actually consist of the processes. So we may have process 1, process 2, or maybe threads and so on. The set of these processes actually is the V, the nodes. And we may also have the resource types as the nodes. So we may have R1, R2 and so on. So these guys, resources and processes, will act as a nodes. And then there will be the edges, okay. E stand for the edges, okay. Now edge can be from the process to the resource, okay, or from the resource to the process. Now depending upon, is it a request edge or it is the allocation edge. I mean, here the processes firstly are shown by the circle. So this is a process, okay, shown by a circle, and resources are shown by the squares. So square is your resource. For example, you have a printers, so this is shown by a square, and inside how many instances of that resource you have. For example, you have 4 printers, so you will have 4 boxes inside this box. It will tell us we have 4 printers. Now we may have only 2, say for example disks. We can show it like this, right? 2 boxes only. We may have only 1, so we may show it like this, okay. Now if this is, say for example process I, if this is, say for example printer, okay. Now this is a printer resource. Now if this is being requested, okay, now there will be an edge from the process to the resource, and this is called as a request edge. So you are requesting it, but it's not being allocated. You want it, but this is not being allocated. But if you have an edge, say for example this is the process P2, okay, say this was process P1, and you have an edge from the resource to the process, so this means resource is being allocated, okay. And we can have an instance. If we have 2 instances, for example here, this instance we can say is being allocated to the process P2, so this is the allocation edge, okay. Some books show this allocation edge as a dashed no, edge. That can also be there, but not necessarily. You can use if the arrow is from the resource to a process, that is being it's allocated. If the edge is from process to the resource, it is the request edge. So you are asking for it, you are not given yet, and this is an edge where we say that this resource is being given to the process P2. Now how to say by using the resource allocation graph that there is a deadlock or not. So firstly, if it contains no cycles, then there can't be any deadlock, okay. And now if there is a cycle, it depends upon how many resources you have. We can say certainly that there is deadlock or not. Say for example we have only 1 resource, okay. Then if there is a cycle, if each resource type is instance 1, then deadlock has occurred, so we are sure the deadlock is there. For example, we say this is a resource and it's having only 1 single instance, okay. Maybe this is a printer, and maybe this is a disk. It's only having a single resource. Now process P1, okay, this resource is allocated to P1 from resource to the process edge, so it is being allocated, and P1 is asking for this from P1 to the resource, so it is the request edge, so it is requesting, it is being allocated, okay. Now there is a process P2. Now this in turn is allocated to the P2, okay. This resource is allocated to P2, and P2 is asking for the so resource 1, so this is resource 2, okay. So resource 2 is allocated to P1, and resource 2 is resource 1 is allocated to P1, and resource 2 is allocated to P2, and P1 is asking for R2, and P2 is asking for R1. So there is a loop, okay. When there is a loop or circle or cycle, and we have only 1 instance, it is a deadlock without any doubts, okay. It is a deadlock. But if we have a multiple resources, okay, then there may be a deadlock or may not be deadlock. So if resource type have multiple instances, the deadlock may exist. That means there may be a deadlock or may not be a deadlock, right? say for example, let us give another example of it. If you firstly see this diagram, there is no cycle, so there is no deadlock. Okay, firstly, if there is no cycle, there is no deadlock whatsoever. So look at this. R2 is being allocated to P1, and P1 is asking for R1. R1 is allocated in turn to the P2, but P2 is not asking the R2, so there is no cycle. In fact, R2 is assigned to the P2, and P2 is asking to the R3, which is being assigned to our P3. Okay, now since there is no cycle, so there is no deadlock. Why? Because P3 is not in a contention. So what will happen is, even we have R4, there is nobody is actually requesting for R4. Now because there is no cycle, no loop, so they can't be in deadlock. See, if R3 is because they are stuck right now, because they can't work, because P1 is asking for R1 to finish, but R1 is being given to P2, and P2 is asking for R3. But R3 is given to the resource 3 is given to the P3, so P2 can't finish, so it will not release the R1. So P1 is asking R1, so R1 is not free, so it can't leave the R2, and so on. So they are stuck but not in a deadlock. So why? Because R3 is being given to the P3, so P3 is not asking for anything, so it's not in a contention, it will finish. So when this process will finish, it will release the R3. Okay, now R3 when released, it will be given to P2, and P2 was only asking for R3 and it's being allocated R2, so it will finish. Okay, when the P2 will finish, it will release the R1 as well as the R2. So when it will release the R1, P1 can go forward and take the R1, and it will finish, and it will release the R2 as well, and all processes are gonna finish, so there is no deadlock at all. Now here we have a cycle. Okay, and because P1 R1 is given to the P1, P1 is asking for R1, R1 is given to P2, but P2 is asking for R3, but R3 is in itself given to P3, which is asking for the R2. Okay, and R2 has two instances of that resource. Say it is a disk, so we have two disks, so there are two resources, and both of them are occupied, and they are in a loop. So P3, if P3 is given R2, then and only then it will release the R3. But it can release it can get R2 only when P1 and P2 finishes. But P1 is waiting for R1, which is waiting for which is given to P2. So P2 is having the is requesting R3, which has been taken by P3. So nobody actually go forward and finish. So they are in a perfect state of deadlock. Okay. And here we have a cycle, so that's why we say that if we have multiple resources, there may be or may not be. Having a cycle doesn't mean there is a deadlock. If we have multiple resources, if we have a single resource and there is a cycle, so it is perfectly a deadlock. Now what about this? Now P1 is asking for R1, even though it has two resources. One is allocated to P2, one is given to the P3. Now P3 is asking for R2, and R2 is given to P1, and it has another resource which is given to P4. Now there is a cycle. Okay, as you could see, there is a cycle, perfect cycle, but it's not a deadlock. Why? Simple reason is because P2 and P4, they are not in a contention, so they will finish. When they will finish, they will release the R2, and this will release the R1. So when the R1 is released, you can give R1 to the P1. Okay, and P1 finishes because it has got the R2. Now it will get the R1, it will finish to release the R2 as well, or P4 will release the R2 as well, so P3 can access that R2, and P3 also finishes, so there is no deadlock. So this was the graphical representation of deadlock, called as a resource allocation graph. Okay, now next we're gonna see the various strategies for handling the deadlock. So this thing we will see in our next video. Okay, until then, ma salam.